Algorithm is a very exciting algorithm that's targeted for quantum computers. It's expected to offer an exponential speedup for factoring large numbers, as compared to the best classical implementation, which involves a guess and check procedure or an exhaustive search for a factor of a large number. Now, why is this important? This is because the factorization problem being hard is something that we depend on for our encryption procedures. Shor's algorithm includes classical and quantum components. So for classical computation, we use Euclid's algorithm for finding the greatest common factor, or GCF, as well as clever math that helps us find factors of coprimes. Here we have the Euclid's algorithm pseudocode, where we take two numbers, A and B, and we attempt to find the greatest common factor between them. So we first see which number is larger, A or B, and we subtract the smaller from the larger. We continue this procedure until A and B are equal, or either A or B is equal to 0. Then we know that we found our greatest common factor. For the clever math that helps us find factors of coprimes, we take two coprime values, so here we'll use x and y, and we raise x to some value p that allows us to find a multiple of y plus 1. So for example, we have two coprimes, 6 and 35. We know they're coprimes because their greatest common factor is 1. And we raise 6 to the 2 to get 36, or 1 times 35 plus 1. So in this example, we know that p is equal to 2 and n is equal to 1. Now as a note, coprime values don't necessarily have to be primes themselves. They just have to be two values where their greatest common factor is 1. The quantum computation in Shor's algorithm involve routines that quickly find p. We're going to look at this in a little bit more depth. Let's review the classical components of Shor's algorithm. We have a large number n, and we hope to factor it. So we first make a guess of the factor, and we'll call that g. We'll use Euclid's algorithm to determine if g shares factors with n. If we find that g shares a factor with n, we're done. That's highly unlikely though. So if not, we are going to find some p to help us find factors of that large number n. So we'll look at this. So if the greatest common factor of g and n is not equal to 1, which is highly likely, we are going to have to find some value p that will allow us to find factors of n. We'll cleverly rearrange this information in the following way. So we know that the greatest common factor of g raised to some p divided by 2 plus or minus 1, and n will equal factors of n. But what is p? Trying to guess values of p is just as challenging as trying to find a factor, especially if n is very large. This introduces the quantum aspect of Shor's to factor n. We have this challenge of finding the right p to find g to the p minus 1 is equal to m times n. But not every p works. For example, we don't want a value of p that produces a multiple of n. We want factors. We also don't want odd values of p because that will produce fractions. We need an integer. So for example, if we had p equal to 1, g to the 1/2 could give us a fraction. So this introduces our quantum solution. We will superimpose possible values for p and use interference to find the correct value of p very quickly. Before we get to finding p, we need to point out some patterns in numbers. So we have g to the p minus 1 equal to m times n, or some multiple of n. Then we can make the substitution that g to the p minus 1 modulus n is going to be equal to 0. So let's rearrange that to get g to the p mod n equal to 1. So as a refresher, the modulus operation, or mod, finds the remainder of division. So here we have 5 mod 3 is equal to 2. In the case of our equation above, we see that if we have g to the p minus 1 equal to m times n, we know that if we divide this by n, we will get a value m, no remainder. So that's how we get the 0 value here. Something to point out that's very important is that the modulus operation repeats with some certain frequency, with some certain period. So here, if we look at 0 mod 3 equals 0, 1 mod 3 equals 1, 2 mod 3 equals 2, 3 mod 3 equals 0, we start to see our values appearing again. So we have 0 again and 1 again. Shor's algorithm takes advantage of this and turns a factoring problem into a period finding problem. So if we look at this equation that we just defined up here, we know that if we have p times some multiple value, so here we have g to the p mod n, g to the 2p mod n, g to the 3p mod n, and so on to some exponent k that's an integer, we will have all of these equal to 1. So we have this repetition that is seen with the modulus operation. With that in mind, we jump to Shor's quantum calculations. We use superposition to test many input values at once. So here we can use our Hadamard operation to create a superposition of candidate p-values. And then with those superpositions, we calculate g to the p mod n. So we calculate all of these values here to find a superposition. Now we need to determine the period or interval between repeated solutions of g to the p mod n equal to 1. Fortunately for us, the quantum Fourier transform, or QFT, can easily find a function's period quickly and efficiently. We're not going to go into depth about the QFT, but I would highly recommend looking at more information about it. The circuit structure is very well known and clearly defined, so it's a building block for many popular quantum algorithms. So here we have our first part of our quantum circuit, our superposition, our calculation of g to the p mod n, and then we use the QFT to help us find the interval at which the answer of 1 reappears. So in this example, for n equal 15 and g equal to 7, we can see that we have a plot here of g to the x, g raised to the candidate p values mod n versus different candidate values for p, so we'll call them x here. And we'll see that the value for p is 4. So the QFT would help us find this value of p equal to 4. So the QFT found value of p equal to 4 for n equal to 15 and g equal to 7. Now with that, we're able to find our factors of n using our original equation that we defined earlier, using g raised to the p divided by 2 plus or minus 1 equal to n times n. So we find the greatest common factor of these two values to find our factor of our large value n. So let's try this out. So 7 raised to the 4 divided by 2 plus or minus 1, and 15, we'll use Euclid's algorithm to find the greatest common factor. We see that 49 plus 1, or 50, and 15, they share a greatest common factor of 5, so a factor of 15 has been found. And then if we do subtraction, 49 minus 1 and 15, 3. So another factor has been found. We can check out the quantum implementation of Shor's algorithm in Qiskit. So here, this is the circuit that actually implements Shor's for our g equals 7 and n equals 15 example. And we can see our components of our calculation, our modulus calculations here, and our QFT here. If you want to do more